Okay, let's look at this. Here's a polar graph. It's kind of pretty, right? And so we want to talk about what would these things mean. So we're gonna hit some. Actually, we're gonna hit some today when we talk. We're gonna hit some really big themes in the course, and this will be like kind of a self-assessment to see if you can answer these like kind of if there were two or three or four things that I want you to get out of this course. We're gonna hit those kind of broad principles today. And here's the first one. The first one is, what would this mean? What would it mean if dx d theta is 3? Say, and dy d theta is, say, -2, and dr d theta was, say, 1/4. So our great hope that after the all semester reviewing, talking about this many, many times, is that you could interpret what this number means 3 if it's dx d theta. So I'm hoping there's lots of confidence in your brains right now. Oh yeah, I know what that means. What does it mean? dx d theta equals 3.
Means for any small change in theta, the change in x is 3 times the change in
3 times the change in yeah?
and theta.
Theta. Right. Good. Okay, so she got it. Given a small change in theta, the change in x would be 3 times as much as that change in theta. Rate of change. How these two quantities are changing relative to each other. X is changing 3 times as fast as theta. So given any change in theta, the change in x will be 3 times as much as the change in theta. All right, where in this graph could that be occurring? So we know that changes in theta are counterclockwise, right? So we go counterclockwise. Where might dx d theta equal +3? So let's look along this first part of the curve. Could dx d theta be +3 along here? Yes or no?
Possibly.
Is it possible that dx d theta could be like +3 somewhere along here?
Yes.
Yes. As we turn counterclockwise, we're going to the right, right? This means to the right. So as theta increases, the graph is moving, the points are successively being plotted in a right direction, which would be positive. What about along this part? Could dx d theta be +3 along here?
No.
Dx d theta would have to be negative here, right? For increasing theta, x is decreasing. All right, what about dy d theta being -2? Could that happen, say, along this part of the curve right here? No. Dy d theta here would be positive. For increase in theta, y is going up. We're going up toward the top of the graph. What about dy d theta equals -2 along here?
Yes.
Yeah.
Yes, because for increasing theta, this is the direction of increasing theta, right? Counterclockwise, y goes down. What about along here? dx d theta, positive or negative? dx d theta.
Negative.
I got one vote for negative. dx d theta.
That would be
I would say positive.
Positive, right?
Oh,
Positive.
yeah, sorry.
Yeah, it's positive because as theta increases, we're heading to the right. So maybe along this part of the curve, right there, is where maybe both these things could be true. There might be a point where both those are true. Right? Maybe somewhere around here. I just made those numbers up, so it's not guaranteed. But, or no, actually more like this. More like somewhere like this, right? dx d theta 3 or dy d theta -2. So somewhere in here. Maybe those would both be true. All right, what does it mean that dr d theta is 1/4? So first of all, just not looking at the graph, but just in general, dr d theta equals 1/4. Somebody knew. What does that mean? dr d theta equals 1/4.
I can go.
Please.
Okay. Given a small change in theta, the resulting change in r is 1/4 times theta.
1/4 times
Theta.
the change in theta, right?
Change in theta.
Yeah, the change in theta that you picked. So you pick a small change in theta. the resulting change in r would be 1/4 as much as the change in theta that you picked, right? So this equation is what characterizes our meaning for that number, the rate of change. Given a small change in theta, change in r, 1/4. Okay, so where might that be? How about, could that be, say along here? What do you think? What does dr d theta look like right there?
Wouldn't it be really high?
Yeah, it's really high, right? So we're just changing theta a little bit, and r is shooting way up. And this seems like more of a smaller rate of change. So maybe more like right here. More like that, right? R is still increasing. We're getting farther from the pole, but just gently, right? Just kind of gradually getting farther from the pole as theta increases. All right, where's another place where dr d theta is 1/4? Maybe somewhere around here. Somewhere through there, dr d theta is going to be 1/4 because you're going away from the pole as theta increases, but just a little, just slightly. Okay, how do we use? All right, how do we find, say, dx d theta and dy d theta? So we did this last time, just as a review then. Where does the function for dx d theta come from?
The function dx d theta comes from when you define x equals r cosine theta.
Right, and in fact, if r is, in this function, r is a function of theta, so r is a function of theta times cosine theta. And then how do we get dx d theta?
Product rule?
Product rule, right? Right, we're going to take the product rule because r is a function of theta, r changes with theta, and then times cosine theta, which gives us x. So we're going to need the product rule to do that. Okay. Where are my questions here? Somewhere there's some questions. Here we go. How do you determine places where the graph is furthest to the left or the right? Like that, and like that, and like that. What's true about those points?
dx d theta equals 0.
Okay, a couple of you said it, right? dx d theta is 0. For a change in theta, x doesn't change, so that's so we're kind of heading vertical for a moment there, right? So right at that moment where theta is changing, x is not changing, only y is changing. We're only going up and down and not left and right. So local leftmost and rightmost points are where dx d theta is 0. What would, how would we get points furthest from the pole? So like, here's a local point that's furthest from the pole. Here's another one. Here's another one. How would we pinpoint those points?
dr d theta equals 0.
Okay, so she wants dr d theta equals 0. What about the rest of you? Agree with that?
Yeah, I agree.
Yeah, right. So like this is kind of like a true local maximum of the polar graph. A local maximum of the polar graph would be like we have a maximum r at a moment, right? And that's going to happen when you're tangent to a constant r. So that means we want dr d theta to equal 0. So r is not going to change for a moment there. So r is increasing, then it holds steady, pauses for a moment, and then decreases. Well, that's going to be a local maximum for the polar graph. So these points furthest from the pole, locally, local maximum, dr d theta. Would be dr d theta equals 0.
I have a quick question.
Yeah, please.
So could dy d theta equal 0 at like the topmost point now?
That's right.
Or it's
Yeah, I just didn't mention that case. if we want the
Okay.
highest point on the graph. So now talking vertically. So there's the idea of highest, biggest in terms of distance from the pole, and that's a matter of r, right?
Oh, okay.
And then there's the matter of highest just vertically on the graph, just going up. That's a matter of the y coordinate, dy d theta equals 0. So that would be like here, dy d theta would be 0. Here, dy d theta is 0. Also local minimums, like lowest. Yes, so when you say a local max, you have to explain what you mean. Do you mean furthest from the pole for a moment, or do you mean highest up for a moment?
Okay. Because the problem I've been having, especially when I try to do dy d theta, is that I'll reach a point where the change in vertical distance or y is 0, like right when it reaches pi or pi
Yeah,
half.
so that's happening here.
Right, yeah, because it's also there, but
Yeah, so
it's
that's
only with double angles I struggle with that.
yeah, so dy d theta equal to 0 and dx d theta equals 0, I should mention that, can also give vertical or horizontal tangents through the pole. Not just, and those will not be local maxes or mins of any type. So like here at pi, or here at pi over 2, we're going to have dx d theta is 0 at pi over 2. Or close to it. And then at pi, we have dy d theta is going to equal 0. So this is negative r's here, reaching theta equals pi. So right there at theta equals pi. Looks like they're somewhere around there. You're going to have a dy d theta equals 0 also. Does that answer it?
Yeah.
Sorry, so at theta, when theta is equal to pi, the r value is not 1, it's 0.
Yeah, so this is 0 to pi over 2, and then pi over 2 to pi. So, yeah, it's not, so somewhere around here, dy d theta looks like it's 0 to me right before pi over 2.
Okay, but you would only know that if you had the equation.
You got to do the math. Yeah.
Okay.
You got to do this thing. Do y equals r theta sine theta, r of theta sine theta. Do the product rule. Set for dy d theta, set it equal to 0. Yeah, but it looks like you got two little places here where dy d theta equals 0. Right before pi and right after pi.
Okay, and then you would plug in like like when theta is equal to pi, and then when theta is equal to pi halves.
No, you're going to solve dy d theta for an angle theta. So you're going to have this, and you're going to set equal to 0, and that's going to give you a theta values where you have.
Oh, right, of course, yeah.
Yeah, you're trying to find those theta values. You're not plugging those in.
Right.
Is that,
Okay, yeah.
Yeah.
That does make sense. Yes.
Okay, sure. All right, so that's kind of an overview of rate of change with polar graphs. Okay, so let's talk about area. So remember when we talked about area, what was the first thing we started with? Area? The first thing we started with was to try to figure out what our, how to write an accumulation of area. Why doesn't it go away? It was going away before. Okay, so we'll do that. So we first looked at that constant rate of change situation of area. So here's a constant rate of change of accumulating area. Right? We had a flat horizontal top to this. And we were interested in what is the rate of change, right? So we wanted to know what is the rate of change of area. So this would be dA dx. And since it's constant rate of change, all we need is 1 dx and corresponding dA. And since this ratio is going to remain constant, all we need is 1 dx and corresponding dA, and that'll give us the rate of change. So right now, what am I showing for dx?
7.
7. Right? Starting from 0, we have a change to x of 7. And what is the resulting change in area when x increased by 7 there?
35.
35. And so therefore, dA dx, since that ratio is going to stay constant, we have constant rate of change, is 35/7 or 5. So the constant rate of change is 5. And then we said, oh, hey, look, that's the height of the function. Remember that? We said the rate of change of area is just the height of the function. Or it's where the area is being added here on the left, and the magnitude of that left face, their left side, is 5, and that's our rate of change. Okay, and then we said, well, what about if the value of the function is changing? So that was for a constant. What about when the value of the function is changing? Well, we want to utilize what we just found. So what we're going to do is we're going to zoom in at any given point of our graph, zoom in, and think about the graph is made up of a lot of little constant function values. And then we want to utilize what we just found. What is the rate of change of area? What did we say? We said dA dx was, so for that first graph, we had constant rate of change. We saw that it was 5. Well, when you have when your function has a changing value, you can just, if you just zoom in far enough and consider little steps, just like this situation. So then what does dA dx equal?
F of x times dx.
Okay, that's what dA equals, but dA over dx would just be
X or
just
Y.
f of x, right? Just the y coordinate, right? It's just the y coordinate, just like it was here. But that would be for small dx, right? We got to keep dx really small so that we can assume that the function is constant over that small change in x. As soon as you make the change in x too big, fx, this value changes too much, and that isn't accurate anymore. But for a small change in x, we can assume we have this case here. And we know that the rate of change was just the value of the function, 5. So for a changing function, we can also assume that the rate of change is the value of the function as long as we assume that, or as long as we keep taking a small enough value of dx. Okay, so we want to do this whole same thing again now in polar coordinates. We want to talk about the rate of change of area for polar coordinates. So we want to start with this case. So in polar coordinates, we have r as a function of theta. What is a case like this? What is a constant function in polar coordinates?
A circle, right?
Naven wants a circle. What about the rest of you? Agree with that?
Yeah.
Yes.
Good,
Yes.
yeah, exactly. So it's going to be a circle centered at the pole. That's going to be our constant function. And so we want to figure out what the rate of change is for that. All right, so clear all the drawings. Let's turn that off. And let's just graph, say, r equals 3. And why isn't that graphing? Oh, it's too light. It's too thin. Let's try line width. Okay, there we go. So there's r equals 3. And so I have r is some function of theta, and it's a constant, 3. So is the rate of change 3? is the rate of change 3 like it was, the value of the function before? So let's figure it out. So now we're talking about dA d theta. So the rate of change, dA d theta. And we said if we have a constant function, then all we need is a particular dA and a corresponding d theta. And since this rate of change is going to be constant, dA d theta is going to be constant, that one correspondence of dA and d theta is enough to get us that rate of change. So let's pick the easiest one we can think of. So, we're thinking here's theta equals 0. And theta turns this way, right? So what change in theta is, and corresponding change in area would be really easy to write down here. So you can pick anything you want because it's a constant rate.
2 pi.
2 pi, good. So let's do theta is, d theta is,
d theta is 2 pi.
2 pi. And what is the corresponding area?
Pi r squared.
Pi r squared. So when you make it all the way around, the area that you sweep out is pi r squared. In this case, pi times 3 squared. And that's corresponding to a change in theta of 2 pi. So we can just set up that ratio, 2 pi r squared, or pi r squared over 2 pi equals 1/2 r squared. So notice, for a constant function, the rate of change of area in polar coordinates is not the value of the function. It's something different here. It's 1/2 r squared. So what about when r is not constant? What about when the function is some function of theta? Well, the same thing again applies. If we take small enough d thetas, we can assume that r is constant. So let me graph something like that. Sure, this one. Okay, so r is not constant, r is changing, but if we take a small enough theta, we can assume and then in fact that's kind of a big d theta, but we'll just go with it. So, but any smaller and I can't make the drawing. So here's my d theta, and I'm going to assume for that d theta that r is constant. Let's try that again. Like that. And then for the next d theta, I'm going to assume r is constant. Trying to mimic the graph. And then the next one, r is constant. And then the next one, r is constant. And then the next one. So I'm just like we had the little horizontal steps for dx's. Now for d thetas, I'm doing constant r values. So in each one of those little d thetas, I have this rate of change because r remains constant. So the rate of change is 1/2, whatever my function is, squared.
Do you mind explaining again how you got, for d theta, you got 2 pi? Is that just because through the whole revolution?
Yeah, we're doing one revolution of the circle.
Okay.
And then because we know that will result in an area of pi r squared, the whole area of the circle.
Oh, okay, I understand.
So these are corresponding change in theta, change in area.
Okay, thank you.
Yeah. All right, so we've got our area. We have our area rate of change of area in polar coordinates. It's 1/2 r theta squared. It's not just the constant r. It's not just the value of the function, r theta. Why? Because theta is not a distance quantity, right? Theta is a change in angle measure, which isn't a distance like dx is. X is distance, horizontal distance. Since theta is not horizontal distance, That's why we get something different than when we did it in rectangular coordinates. Okay, any questions on that? So we're developing the rate of change of area, accumulated area in polar coordinates. So let's look at an example. This one. Okay, so let's, we have time? Oh yeah, we have time. So first of all, let's practice. I want you to practice, because this is super important. I've got two functions here. G theta is cosine theta plus 1. And f of theta is 5 cosine theta minus 2. And for practice, can you sketch these graphs just for from 0 to pi over 2? So sketch both. No technology. This is on the final. It's sketching without technology. Sketch both for 0 less than or equal to theta less than or equal to pi over 2. You have lots of practice in your homework. We've done it on 2 different days. So we'll do it one more time here. So just the first quadrant, 0 to pi over 2. Can you sketch these graphs? Cosine theta plus 1, 5 cosine theta minus 2. Go. All right, so you're working on this. Hopefully you still have some copies of that polar graph paper. That's really helpful for doing your homework and practicing and taking notes. So if you got the polar graph paper, use that. Here's the graph of cosine theta plus 1. You should be able to sketch that. That's just the cosine graph moved up 1, so it goes from 0 to 2, the midline of 1. And basically for that one, r is just going to decrease from 2 to 1, slowly at first and then rapidly. For this one, 5 cosine theta minus 2, that has a midline of minus 2. It has a maximum then of 3, 5 more than minus 2, and a minimum of minus 7, which is 5 less than minus 2. And the cosine starts at the max. So when we get to pi over 2, we'll be at the midline minus 2. So this function will start at 3 and decrease to minus 2 by the time it gets to pi over 2. So somewhere before pi over 2, it's going to cross through the pole and go into negative r territory. So let's see these graphs here. So I don't know how far you made it. We need to move on. Hopefully you made some progress. But our the f function starts at 3, and the g function starts at 2, and they both decrease. At some point they're going to intersect because f is decreasing more rapidly. And the f function is the red one, or sorry, g is the red one, and that's decreasing from 2 to 1. So it's going to end up at 1 here, at pi over 2. While the other one, before pi over 2, is going to hit the pole, like we said, 0, right here. And then it's going to go into negative territory and hit negative 2 by the time we get to pi over 2. Okay, so if you didn't get all that in that short time, that's fine. Hopefully you made some positive progress. But given more time, these are both definitely fair questions to ask you with all the practice we've had with this. Any questions on sketching those polar graphs? Okay, cool. So let's write, I want to write the area accumulation function for G. And so let's take a look at that. So I want to know the accumulation of area with respect to theta for the function g, something like this. So can you write it? So here's this other, and last day of the semester, hopefully everyone can do this. I'm going to write the accumulation of area in the polar graph of g, like I'm showing there in red. So accumulated area as theta increases. So let's call that, say, A sub g, theta. This is the area from, before rectangular coordinates, it was the area from the graph to the x-axis. Now it's from the graph to the pole, right? So r equals 0 is the pole. So we get these kind of pie shapes, pie piece shapes, as we accumulate area in polar graphs. So can you write the net accumulation of area as a function of theta?
Wouldn't it be the integral of 1/2 cosine theta plus 1 squared?
All right, so you want the integral? So integral, right, net accumulation, integral, right, net accumulation. It's like one of the most, if not the most important thing of the course, net accumulation, integral from what to what?
0 to theta.
0 to theta, good. And then the first student who was, sorry, what did you say the integrand was?
I said it was 1/2 cosine theta plus 1 squared.
And then?
dt.
Okay, good, right? So dt, but then we'd also need what?
Cosine of t.
T, right? So this is, yes. So it'd be 1/2 r squared. We said that was our rate of change, right? We found the rate of change for polar area was 1/2 r squared. So the last thing we just need to do is get that in terms of some other variable. And let's go ahead and use u. We've been using t for parametric functions. So I'm just going to go ahead and use u. Okay, very good. So that's our, that would be the accumulation of area. Oops. From the graph of G to the pole. So what if I want to find, how do I represent that amount of area right there? What is that area right there?
It would be the integral from 0 to pi over 2, and then half cosine t plus 1 squared dt.
Okay, can I write that any more succinctly? That's right.
A sub g pi over 2.
Right. Function notation, another huge theme in this course. Function notation represents the value of the dependent variable. So in this function, areas, dependent variables areas, so we use function notation to write that. So that's AG of pi over 2 is that area that I'm showing right now, all the way from 0 to pi over 2. And then yes, and then this would be a nice trig integral. We could expand that. We'd have cosine squared, 2 cosine, and 1, and we can do that. We know how to do that integral, so we could get this area by hand. We're not going to take the time to do it, but that's well within the scope of things we learned. How do you do the integral of cosine squared u, for instance? Does anyone remember what was the technique for that?
Using a trig identity,
Yeah, which ones? Do you remember what trig identity it was?
the half angle.
Good. If it's just cosine squared or just sine squared and nothing else except, constant factors are fine. But no other sine or cosine expressions multiplied. If it's just solely cosine squared, that's the half angle identity. Hopefully that at least is familiar. Okay, and that would be using that would be part of solving this one by hand. Okay, so new one here. So here we go, doing good. Now I want to write a new function, this accumulation function. So it starts It starts by accumulating f like this. I'm sorry, g. Accumulating area within the function of g. But then when it gets here, we start accumulating inside f. Did you see it? So this is what I want. I want the accumulation of area was in the polar graph like that, but then when we get to that intersection point, then accumulating like that. So we'll call this I'll just call this one a sub 1. How am I going to do that? How am I going to accumulate area? So basically what I'm saying is I want to accumulate area inside of this defined region. I want to accumulate area inside this defined region right there.
Could you try by finding the intersection point of the two functions and then accumulating from 1 theta to the intersection point and then from the intersection point to pi hat?
Okay, good. Did you catch that? So, right. So what will the structure of our function be then? To do that accumulation within that region right there. What will the structure of the function be?
Your piecewise function.
It's going to be piecewise, right? First, and what's the first piece going to be?
It's going to be from 0 to
But
whatever the intersection point is.
Yeah, but what will the function be? What will the area accumulation function be in this first part?
A sub g.
Yeah, the one we already found, right? So at the beginning, it's the same. So we can just write that down. So we're going to have a piecewise function. And at the beginning, it's just going to be a sub g of theta. And that's when theta goes from what to what? 0 to when do we stop accumulating on AG? Here.
Do we set the functions equal to each other to find the intersection point?
Yeah, we're going to need this. What is this angle, right? So what is this angle right here? Where we're going to stop accumulating according to G and start accumulating according to F. So what's true? The R values are the same. So my G theta, we're interested in where is G theta equal to F theta. My R is to be equal. So that's cosine theta plus 1 equals 5 cosine theta minus 2. And so we're going to get 4 cosine theta equals 3. And so cosine theta equals 3/4. And theta equals the inverse cosine of 3/4. Which we get by setting the r's equal. So this over here is going to be cosine inverse of 3/4. Okay, and then how are we gonna then what are we gonna do? So now we got the AG up till that point, and then we need the accumulation to start according to F. So how will we do that?
A sub g of our cosine 3/4 plus the integral of our cosine 3/4 to theta.
So now we're going to start accumulating from arc cosine of 3/4 to theta. And then what will our rate of change for that one be?
1/1 2 multiplied by f of t squared.
Right, so we're going to accumulate, this blue region here is accumulating according to the area according to the f function. So it'll be 1/2 f of t squared dt from our intersection point to theta. But I want all the accumulation starting from 0. So I want to keep accumulating area just like continuously here. So we don't want a cosine of at this angle, we don't want it to start over at 0. This would at that intersection point will give us 0 accumulated area at that intersection point. So what did she say? She said we also need
a sub g of inverse cosine of 3/4.
Good, right? We need everything, and we could even do a1 here because a1 is defined there. So I could do ag or a1. Let's just do this. And that would be from what? That would be from cosine inverse of 3/4 less than or equal to theta. Where you got less than or equal to. There's some other angle here. We're not going to find it. The other angle where f equals 0. I actually have it here. But you would take the f function and set it equal to 0, and that would be where it goes through the pole. That would be where this would end. And that's arc cosine of 2/5. That's enough. And that's pretty easy to see. Arc cosine of 2/5 is where that thing equals 0. And so there we got it. We got the accumulation of area for that region. That's the red plus the blue, accumulating from 0 all the way to arc cosine of 2/5. So there's our what? It's like our total accumulation, right? All the accumulated area from before, the red, plus the new net accumulation of the blue function. Super important concept from this course, right? All previously accumulated, this is total accumulation, previously accumulated as a lump sum, plus new accumulating area in the blue region. And then what would we do to get the whole thing? I want to get the area of that whole kind of shark fin shape. How would I represent that?
You could do a sub 1 of pi over 2.
Not pi over 2. But
Is it
Would
just
be
arc
a
cosine?
sub?
Sorry.
You can go ahead.
Or what, is it going to just be arc cosine of 2/5?
yeah, right, because at 2/5 is when that f function gets to the pole. So it's a little bit before pi over 2. A little bit before pi over 2. Right there. So that whole area then would be a sub 1 of arc cosine of 2/5. Will give us that whole area. Okay, one more thing. Quick, any questions on the piecewise accumulation function? All right, what about this? What about this area? I want to accumulate this area here, purple. How would I do that?
You would do the accumulation function for that's
We'll call this A2.
Oh yeah, A2. So how I would personally find it is I would do the accumulation function for f of theta, and then subtract it from and then subtract a1 from it.
AG? AG, right?
Yeah.
Right, it's going to be the accumulation function for f minus the accumulation function for g. But we can make that into one integral by just subtracting the rates of change. So it'll be 1/2 f of u squared minus 1/2 g of u squared, which is the same thing as this, the accumulation according to f minus the accumulation according to g. We could just subtract the rates of change, and that will do it also. So that will give us the accumulation of area between the graphs, right? Like outer versus inner. Okay, questions on that?
The area that's like going along the y-axis at the bottom, that doesn't get accumulated at all, right? 'Cause it's between the x that we accumulate.
Y-axis. I don't know what you mean.
That
over here?
Yeah, that
This
doesn't.
is for angles greater. So this would only, so after we cross this point, for this one, after we cross this point here, then it's kind of, we'd have to talk about what would happen. I think it would be like a net area, right? It would be like area would start subtracting since f now is greater, f now is less than u. So this would just be for this part here. We would get positive area. So then if we kept going past that point, then it would be like a net area situation where this would start decreasing according to how much area is between them after that.